Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why some planets have no moons. Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons, while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers. But these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the Sun, or get ejected from the system entirely. The closer the planet is to the Sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are 3 primary mechanisms. Co-formation, where the moon forms from the same disk of material as the planet. Capture, where the planet's gravity snares a passing object. And giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the Moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter. Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across and Deimos about 12 kilometers. Mars likely captured them during the early solar system when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the Sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely formed their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young Sun. These disks contained enough material to form multiple large moons. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons, moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where Hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. Why some objects in space are heavier than others. When you hold a rock in one hand and a piece of styrofoam the same size in the other, The difference is immediately obvious. The rock is heavier. This difference comes from density, the amount of mass packed into a given volume. The same principle operates throughout the universe, but on cosmic scales, the variations in density become far more extreme than anything we encounter in daily life. Understanding why some objects in space are heavier than others means understanding how matter behaves under different conditions of temperature, pressure, and gravity, and how the history of an object determines what it's made of, and how tightly that material is packed together. Start with the simplest objects in space, clouds of gas in the interstellar medium. These clouds are extraordinarily diffuse, containing perhaps only a few atoms per cubic centimetre. In comparison, the air you breathe contains about 25 billion molecules per cubic centimetre. The density of interstellar gas is so low that the best vacuum we can create on Earth is still millions of times denser. These gas clouds have mass, sometimes thousands or even millions of times the mass of the Sun, but it's spread across such enormous volumes that the density is essentially zero by any terrestrial standard. Planets show a wide range of densities depending on their composition and formation history. The gas giants Jupiter and Saturn are primarily hydrogen and helium, the lightest elements. Jupiter's average density is about 1.3 grams per cubic centimetre, only slightly denser than water. Saturn is even less dense at 0.7 grams per cubic centimetre. It would float in a bathtub if you could find one large enough. This low density reflects their composition, dominated by the lightest elements in the universe, compressed by their own gravity, but not enough to create extremely high densities. The rocky planets of the inner solar system are much denser. Earth has an average density of 5.5 grams per cubic centimetre, about 4 times denser than Jupiter, despite being much smaller. This difference comes from composition. Earth is made primarily of rock and metal, silicates in the mantle and crust, iron and nickel in the core. These materials are intrinsically denser than hydrogen and helium. Silicon, oxygen, magnesium, and iron atoms are much more massive than hydrogen atoms, and when they bond together into minerals and metals, they pack together more tightly than gases can. Mercury, the innermost planet, is even denser than Earth at 5.4 grams per cubic centimetre, despite being much smaller. For a small planet, this density is surprisingly high, and it tells us that Mercury must have an unusually large iron core relative to its size. The leading theory, developed by planetary scientists studying how planets form, suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core, with only a thin shell of rock surrounding it. The iron, being much denser than rock, gives Mercury its high density. White dwarfs represent a dramatic jump in density. These are the remnants of stars like the Sun after they have exhausted their nuclear fuel and shed their outer layers. What remains is the core, compressed by gravity but supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth, creating densities around 1 million grams per cubic centimetre, or 1 metric ton per cubic centimetre. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This represents matter compressed to the point where atomic nuclei are essentially touching, with electrons flowing between them in a degenerate electron gas. Subramanian Chandrasekhar calculated in the 1930s that there's a maximum mass for white dwarfs, about 1.4 times the Sun's mass, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and further collapse occurs. This calculation, which earned Chandrasekhar the Nobel Prize decades later, explained why some stellar remnants become something even denser than white dwarfs. Neutron stars take density to an even more extreme level. When a massive star's core collapses in a supernova, if the core's mass exceeds the Chandrasekhar limits, but is below about 3 solar masses, it compresses beyond the point where electron degeneracy can support it. The electrons are forced into the protons, combining through inverse beta decay to form neutrons. The result is a neutron star, a sphere about 12 miles across containing 1 to 2 solar masses. The density at a neutron star's center reaches about 500 million to perhaps a billion tons per cubic centimeter. This is comparable to the density inside an atomic nucleus, meaning a neutron star is essentially a single gigantic nucleus held together by gravity rather than the strong nuclear force. At these densities, matter behaves in ways impossible to replicate in laboratories. The neutrons exist in a superfluid state with zero viscosity. The outer crust is a crystalline lattice of neutron-rich nuclei. Deeper down, neutrons drip out of nuclei and flow freely. At the very center, densities might exceed that of atomic nuclei, and matter might transition into exotic states, quark-gluon plasma, where neutrons dissolve into their constituent quarks, or other forms of matter predicted by quantum chromodynamics, but never observed. Black holes represent the ultimate extreme of density, though their density is somewhat paradoxical. The matter that forms a black hole collapses to a singularity, a point of infinite density, where general relativity predicts that space-time curvature becomes infinite. The singularity is hidden behind the event horizon, and we can meaningfully talk about the average density within the event horizon. For stellar mass black holes formed from collapsed stars, this average density is extraordinarily high, but for supermassive black holes containing millions or billions of solar masses, the event horizon is so large that the average density within it can be quite low, sometimes less than water for the largest black holes. This doesn't mean the black hole's interior is actually that density, just that if you calculated density by dividing total mass by the volume enclosed by the event horizon, you would get that number. The density variations we observe in the universe reflect the different physical processes that create and shape cosmic objects. Gas clouds have low density because gravity hasn't compressed them significantly. Thermal pressure from their temperature balances gravity, maintaining their diffuse state. Planets have intermediate densities determined by their composition, which depends on where they formed in the protoplanetary disk and what materials were available. Rocky planets formed close to their stars where it was too hot for ices to condense, while gas giants formed farther out, where ices could exist and helped build massive cores that captured hydrogen and helium. Stellar remnants have high densities because they are supported not by thermal pressure, but by quantum mechanical degeneracy pressure. As physicist Wolfgang Pauli explained in formulating the exclusion principle in 1925, fermions, particles like electrons and neutrons, cannot occupy identical quantum states. When you try to compress them, they resist because there are no available quantum states for them to occupy. This quantum pressure can support matter to much higher densities than thermal pressure can, but only up to certain limits determined by the mass and the type of fermion providing the support. Temperature also affects density. Hot gas is less dense than cold gas at the same pressure because the particles move faster and push outward more strongly. This is why hot air rises. It's less dense than the cooler air around it. In space, hot gas in the coronas of stars or in galaxy clusters has lower density than cooler gas in molecular clouds, even when both regions have similar pressures. The Sun's core, where temperatures reach 27 million degrees Fahrenheit, has a density of about 150 grams per cubic centimeter, dense by terrestrial standards, but far less dense than a white dwarf, even though the Sun's core is much hotter. The difference is that the Sun is supported by thermal pressure from ongoing nuclear fusion, while a white dwarf is supported by electron degeneracy pressure after fusion has ceased. Composition fundamentally determines the density any object can achieve under given conditions. Hydrogen, the lightest and most abundant element, naturally produces lower density objects than heavier elements. This is why gas giants, primarily hydrogen, are less dense than rocky planets made of silicon, oxygen, and iron. But composition interacts with pressure in complex ways. Under the extreme pressures inside Jupiter, hydrogen is compressed into a metallic state, denser than solid hydrogen would be under normal conditions, though still less dense than rock or metal. The formation history of an object determines both its composition and its density. Early in the solar system's formation, different materials condensed at different temperatures as the protoplanetary disk cooled. Close to the Sun, only metals and rocks could condense. These became the rocky planets. Farther out, where temperatures were lower, water ice could condense, providing additional solid material that helped build larger cores. These larger cores could then capture hydrogen and helium gas before the solar wind swept it away, forming gas giants. Farther still, at the coldest reaches, methane and nitrogen ices could condense, contributing to objects like Pluto and other Kuiper Belt objects. The history of compression matters too. Jupiter's core is thought to be compressed rock and ice, squeezed by the weight of the hydrogen and helium above it, to pressures millions of times Earth's atmospheric pressure. Under these conditions, materials that started as ordinary rock and ice are compressed to much higher densities, possibly exceeding even the density of iron under normal conditions. The exact state of matter under such extreme pressures remains uncertain. Laboratory experiments can replicate some of these conditions, but not the combination of extreme pressure, temperature, and scale found in giant planet interiors. Rotation affects density distributions within objects. A rapidly spinning object experiences centrifugal forces that cause it to bulge at the equator and flatten at the poles. This changes the density distribution, making the equatorial regions less dense and the polar regions denser. Saturn, spinning rapidly and composed largely of fluid, shows a noticeable oblate shape. Its equatorial diameter is about 10% larger than its polar diameter. Neutron stars spinning hundreds of times per second bulge significantly at their equators, altering their density distributions and affecting how they emit radiation. Throughout the universe, from the near vacuum of intergalactic space containing less than 1 atom per cubic meter, through the varied densities of planets, stars, and stellar remnants, to the extreme densities of neutron stars and the singularities within black holes, density varies by factors of hundreds of billions of billions. These variations reflect the different conditions under which matter exists, the temperatures, pressures, compositions, and quantum mechanical states that determine how tightly matter can be packed together, creating the extraordinary range of cosmic objects we observe, each with its own characteristic density, telling the story of how it formed and what forces shape its structure. Why alien life might not use DNA, deoxyribonucleic acid, is the molecule of heredity for nearly all life on Earth. From bacteria to blue whales, from mushrooms to sequoia trees, every organism uses DNA to store genetic information, to pass traits from parents to offspring, and to direct the construction of proteins that build and maintain living cells. DNA's structure is elegant and famous, a double helix of 2 strands twisting around each other, each strand composed of a sugar phosphate backbone with 4 types of bases attached in sequences that encode genetic instructions. DNA seems so fundamental to life that it's easy to assume it must be universal, that any living thing anywhere in the universe would use DNA. But this assumption is almost certainly wrong. DNA is not the only molecule capable of storing and transmitting genetic information, and the specific chemistry that makes DNA work on Earth might not be optimal or even possible under different planetary conditions. To understand why alien life might not use DNA, We first need to understand what DNA actually does and what properties make it suitable for its role. DNA serves three critical functions. First, it stores information. The sequence of bases along the DNA strand encodes instructions for building proteins and regulating cellular processes. Second, it replicates. DNA can be copied with reasonable accuracy, allowing genetic information to be passed from one generation to the next. Third, it allows variation. Copying isn't perfect, and occasional errors introduce mutations that create the genetic diversity necessary for evolution. But DNA is not unique in performing these functions. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information, be copied, and undergo evolution despite having different chemical structures than DNA. These molecules use different sugars in their backbones, 3-Os instead of deoxyribose, locked nucleic acids with modified sugars, or even molecules with completely different backbone structures. These XNAs can form base pairs, store sequences of information, and be replicated by specialized enzymes. They demonstrate conclusively that DNA is not the only possible genetic molecule, merely the one that happened to work on Earth. The chemistry of DNA is optimized for Earth's conditions. DNA is stable in liquid water at temperatures roughly between 0 and 40 degrees Celsius, the temperature range where most Earth life operates. The hydrogen bonds holding the two strands together are strong enough to keep the double helix intact, but weak enough that the strands can be separated for copying. The sugar phosphate backbone is stable in water at neutral pH, but can be broken down by enzymes when necessary. The bases, adenine, thymine, guanine, and cytosine, are moderately stable molecules that can withstand normal cellular conditions, but can be damaged by extreme heat, intense radiation, or strongly acidic or alkaline environments. On a planet with very different conditions, DNA might not function well or at all. Consider a world much hotter than Earth, perhaps a planet orbiting very close to its star, with surface temperatures exceeding 100 degrees Celsius, but with liquid water kept stable by extreme atmospheric pressure. At these elevated temperatures, DNA becomes increasingly unstable. The hydrogen bonds holding the two strands together weaken and break more easily. The chemical bonds in the bases and the backbone break down more rapidly. Organisms on such a world would need genetic molecules more heat-resistant than DNA, perhaps with stronger chemical bonds, more stable base structures, or completely different architectures that maintain integrity at high temperatures. Some Earth organisms that thrive in extreme heat have evolved DNA repair mechanisms that constantly fix damage to their genetic material, but there are limits to how hot DNA can tolerate. Beyond a certain temperature, the rate of damage exceeds the capacity of repair mechanisms to fix it. Alien life on a hot world might evolve an alternative genetic molecule with inherently greater thermal stability, perhaps using bases with stronger bonding, or sugars that resist thermal degradation, or entirely different building blocks that remain stable at temperatures where DNA would fall apart within seconds. At the opposite extreme, very cold worlds present different challenges. DNA becomes more rigid at low temperatures, making it harder to separate the strands for copying. The enzymes that copy DNA become less efficient or stop working entirely when too cold. Life on an extremely cold world, perhaps on a moon like Titan, where temperatures hover around -180 degrees Celsius, would need genetic molecules that remain flexible and functional at these frigid temperatures. The chemistry would necessarily be different from DNA, which was shaped by evolution to function in Earth's moderate temperature range. The solvent environment profoundly affects what genetic molecules are possible. DNA functions in liquid water, and its chemical properties are specifically suited to aqueous environments. The sugar phosphate backbone is hydrophilic, attracted to water, which helps keep DNA dissolved in cellular fluids. The bases are hydrophobic, repelled by water, which helps drive base pairing by pushing bases toward each other and away from the surrounding water. This balance creates DNA's structure and stability. In a different solvent, liquid methane, liquid ammonia, or something even more exotic, DNA's chemistry wouldn't work the same way. Water's polarity, its hydrogen bonding capacity, its ability to dissolve certain substances while excluding others. All these properties shape how DNA behaves. In liquid methane, a non-polar solvent, molecules that are hydrophobic in water might become soluble, while hydrophilic molecules might be insoluble. A genetic molecule designed for a methane-based solvent would need completely different chemical properties than DNA, perhaps with non-polar groups exposed to interact with the methane solvent, and polar groups hidden in the molecule's interior. The availability of raw materials constrains what genetic molecules can be built. DNA requires phosphorus, nitrogen, carbon, oxygen, and hydrogen. Phosphorus, though essential for DNA's backbone, is relatively rare in the universe compared to lighter elements. A planet poor in phosphorus might not be able to build DNA-like molecules and would need to evolve genetic systems based on more abundant elements. Perhaps silicon could replace phosphorus in the backbone, or sulfur could play a role, or arsenate, a chemical similar to phosphate, might substitute. Though experiments with arsenate-based DNA on Earth showed it's much less stable than normal DNA. The 4-base system used by DNA, adenine, thymine, guanine, and cytosine, is not the only possible coding scheme. RNA, DNA's chemical cousin, uses uracil instead of thymine, demonstrating that the specific bases aren't fixed. In principle, genetic molecules could use 3 bases, or 6, or even more. More bases would allow more information to be encoded in shorter sequences. With 4 bases, each position in the sequence can encode 2 bits of information, but with 8 bases, each position could encode 3 bits. An alien genetic system might use more or fewer bases depending on what works best with its chemistry. Some scientists have even created expanded genetic alphabets, DNA-like molecules with additional base pairs beyond the natural 4. These synthetic genetic systems can store more information per unit length than natural DNA and can be copied by modified enzymes. The existence of these expanded alphabets demonstrates that the 4-base system is not uniquely optimal, but rather reflects the specific chemistry that evolved on Earth. Alien life might independently evolve genetic systems with different numbers of bases encoding information in different ways. The structure of the genetic molecule might differ radically from DNA's double helix. DNA forms a helix because of how the bases pair and how the sugar phosphate backbone bends, but other structures are possible. Some XNAs form helices with different geometries, left-handed instead of right-handed, wider or narrower than DNA, with more or fewer base pairs per helical turn. Some synthetic genetic molecules don't form helices at all, but adopt completely different 3-dimensional structures. An alien genetic molecule might be a triple helix, a quadruple helix, a ladder without a twist, or some topology we haven't imagined. The copying mechanism might also differ. DNA is copied by enzymes called polymerases that move along the DNA strand, reading the sequence and creating a complementary new strand. This process requires a complex molecular machinery that evolution has refined over billions of years on Earth. Alien life might evolve completely different copying mechanisms, perhaps catalytic RNA-like molecules that copy themselves without protein enzymes, or inorganic crystals that template the formation of complementary structures, or even copying processes that don't involve template-directed synthesis at all, but rather some form of self-assembly guided by the genetic molecule structure. The rate of mutation, how often copying errors occur, affects evolution's pace. DNA polymerases on Earth make errors at a rate of roughly 1 mistake per billion bases, copied for the most accurate enzymes, though rates vary. This error rate is low enough to preserve genetic information across generations, but high enough to generate the variation necessary for evolution. Alien genetic systems might have very different error rates. A system with much lower error rates would evolve more slowly, potentially making adaptation difficult. A system with higher error rates might generate variation faster, but risk genetic information degradation. The optimal error rate depends on generation time, selection pressure, and environmental stability. RNA represents an alternative genetic molecule that exists on Earth and might have preceded DNA in evolution. RNA can store information, catalyze chemical reactions, and replicate all functions DNA cannot perform alone. The RNA world hypothesis proposes that early life used RNA as both genetic material and catalytic molecule before DNA and proteins evolved. An alien world might develop life that remains in an RNA world-like state, never evolving DNA, or might evolve RNA into forms more sophisticated than anything on Earth, creating genetic systems based on elaborate RNA structures rather than DNA. Some scientists have speculated about non-molecular genetic systems. Perhaps information could be stored in the crystal structure of inorganic minerals, with patterns of inclusions, defects, or layering encoding information that could be replicated when crystals grow and form templates for new crystals. Or perhaps information could be stored in magnetic domains in iron-rich minerals, with the orientation of magnetic fields encoding genetic instructions. These ideas are highly speculative and face enormous challenges. How would such systems be read and translated into functional structures? But they illustrate that genetic information storage might not require organic molecules at all. The universality of certain aspects of information storage might transcend specific chemistry. Any genetic system, whether based on DNA, XNA, RNA, or something entirely different, must be able to store discrete, sequential information, symbols arranged in order that can be read and interpreted. This is fundamentally a problem of information theory rather than chemistry. The specific physical substrate that stores the information might be less important than the information itself, and the mechanisms for reading, copying, and translating it into functional structures. If we ever detect alien life, determining its genetic system would be among the first questions we'd want to answer. If alien life uses DNA with the same 4 bases and same genetic code as Earth life, it would suggest either that DNA is universally optimal, unlikely given all the possible alternatives, or that Earth life and alien life share a common origin, perhaps through panspermia. The hypothesis that life can spread between worlds via meteorites or comets. Finding alien life with completely different genetic molecules would confirm that life can independently originate using different chemistry, revealing that DNA is merely one solution among many to the problem of heredity. The genetic code, the mapping between base sequences and amino acids, might also differ. Earth's genetic code is nearly universal across all life, with 3 base sequences called codons specifying which amino acid to insert when building proteins. But the specific assignment of codons to amino acids appears somewhat arbitrary. There's nothing inherent in the chemistry of the codon UUU that demands it code for the amino acid phenylalanine rather than some other amino acid. The code seems to be a frozen accident. Once it was established early in evolution, changing it would be catastrophic because it would alter the meaning of every gene, so it became locked in place. Alien life would likely evolve a completely different genetic code, with different codon assignments, and possibly even a different codon length. 2 base codons, or 4 base codons, or variable length codons. Why alien life might not use DNA comes down to DNA being a solution specific to Earth's conditions: liquid water at moderate temperatures, specific pH ranges, availability of particular elements, and the accidents of chemical evolution that occurred during life's origin on our world. Different conditions would favor different molecules, and even similar conditions might allow evolution to discover different solutions. DNA is remarkable and elegant, but it's not magic or inevitable. It's chemistry, sophisticated, evolved chemistry that works beautifully on Earth, but that represents just one possible answer to the fundamental question of how to store, copy, and transmit genetic information across generations. Across the universe, life might employ countless different genetic systems, each one adapted to its world's unique conditions, each one encoding information and enabling heredity through different molecular mechanisms, proving that while the principle of heredity might be universal wherever life exists, the specific molecular machinery implementing that heredity can vary as widely as the diversity of worlds themselves, with DNA being merely Earth's particular solution to the universal challenge of passing genetic information from parent to offspring through the generations. Why distant galaxies? Look red. When astronomers point their most powerful telescopes toward the deepest reaches of space, photographing galaxies billions of light years away, they notice something remarkable. These distant galaxies appear distinctly redder than nearby ones. Light that was emitted as ultraviolet or blue has been shifted toward red and infrared wavelengths by the time it reaches Earth. This redshift is one of the most important observations in all of astronomy, providing direct evidence for the expansion of the universe and allowing astronomers to measure cosmic distances and trace the history of the cosmos back nearly to the Big Bang itself. The primary cause of this reddening is cosmological redshift, a consequence of the universe's expansion. This phenomenon was first observationally established by Edwin Hubble in 1929, though the theoretical groundwork had been laid by several physicists, including Alexander Friedmann and Georges Lemaitre, who independently developed solutions to Einstein's equations of general relativity that predicted an expanding universe. Hubble observed that distant galaxies showed spectral lines, the characteristic fingerprints of elements absorbing or emitting light at specific wavelengths, shifted toward longer, redder wavelengths. Moreover, he found that more distant galaxies showed larger redshifts, establishing what became known as Hubble's law. The recession velocity of a galaxy is proportional to its distance. The expansion of the universe is not like objects moving through space. It's space itself that's expanding. Imagine the universe as the surface of a balloon with galaxies painted on it. As you inflate the balloon, the surface stretches and the distance between any 2 points on the surface increases. The galaxies themselves don't move through the rubber. The rubber itself expands, carrying the galaxies apart. This is fundamentally different from regular motion through space, and it's this expansion of space that creates cosmological redshift. When a galaxy emits light, that light begins its journey through space toward Earth. The light consists of electromagnetic waves, oscillating electric and magnetic fields propagating through space. As the light travels, the space through which it's traveling is expanding. This expansion stretches the wavelength of the light. Imagine a wave painted on a rubber band. If you stretch the rubber band, the wave gets stretched too, its wavelength increasing. The same thing happens to light traveling through expanding space. Light that began as ultraviolet with a wavelength of 300 nanometers might arrive at Earth as visible red light with a wavelength of 600 nanometers if it has traveled through enough expanding space. The amount of redshift depends on how much the universe has expanded during the light's journey. Astronomers quantify this using the redshift parameter, represented by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. Wavelengths have stretched by a factor of 2. A redshift of Z equals 2 means the universe has tripled in size. Wavelengths have stretched by a factor of 3. The highest redshift galaxies yet observed have redshifts around Z equals 13 to 14, meaning the universe has expanded by a factor of about 14 or 15 since those galaxies emitted the light we now detect. These galaxies existed when the universe was only a few 100 million years old, less than 3% of its current age. For nearby galaxies, the redshift is small, perhaps z equals 0.01 or less. The Andromeda Galaxy, our nearest large galactic neighbour, actually shows a blue shift rather than a redshift, because it's moving toward us through space faster than the cosmic expansion is carrying it away. But for galaxies more than a few 100 million light-years distant, cosmological redshift dominates, and the farther the galaxy, the larger the redshift. This relationship between distance and redshift allows astronomers to use redshift as a distance indicator. By measuring the redshift of spectral lines in a galaxy's light, they can calculate how far away it is and how long ago the light was emitted. A galaxy at z equals 1 is seen as it was about 8 billion years ago, when the universe was roughly half its current age. A galaxy at z equals 6 is seen as it was less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first generations of stars were forming. Redshift affects all wavelengths equally, in terms of the stretching factor. Ultraviolet light gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into far infrared and eventually into microwaves. For the most distant galaxies, light that was emitted in the ultraviolet, the signature of hot, young stars, arrives at Earth as infrared radiation. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the early universe. They can detect the stretched light from the most distant galaxies, galaxies so far away that their visible light has been redshifted entirely out of the visible spectrum. There's another related effect that makes distant galaxies appear redder beyond just the stretching of wavelengths. As light loses energy through redshift, longer wavelengths mean lower energy. The apparent brightness of the galaxy dims. A galaxy at high redshift appears fainter than it would if there were no cosmic expansion. Additionally, the rate at which photons arrive is reduced. If a galaxy emits 1 photon per second toward Earth, but the universe doubles in size during the light's journey, those photons arrive spread out over 2 seconds because the space between them has been stretched. This reduces the detected brightness even further. The cosmic microwave background radiation provides the most extreme example of cosmological redshift. This radiation was emitted when the universe was 380,000 years old, at a temperature of about 3,000 Kelvin. At that temperature, matter emitted primarily visible and infrared radiation. The redshift since that time is about c equals 1,100, meaning the universe has expanded by a factor of 1,100. Wavelengths have been stretched by the same factor, so light that was visible orange or red has been stretched into microwave radiation. The temperature corresponding to this radiation has dropped by the same factor, from 3,000 Kelvin down to 2.7 Kelvin today. It's important to distinguish cosmological redshift from Doppler shift, though they're related and can sometimes be confused. Doppler shift occurs when a light source moves through space toward or away from an observer. An approaching object's light is blue shifted, compressed to shorter wavelengths, while a receding object's light is redshifted. This is the effect that changes the pitch of a siren as an ambulance approaches and then passes you. For galaxies with relatively small redshifts, say z less than 0.1, cosmological redshift and Doppler shift give nearly identical results and can be treated interchangeably for many purposes. But for high redshifts, the distinction matters. Cosmological redshift is fundamentally about the expansion of space itself, while Doppler shift is about motion through space. Redshift also allows astronomers to study the history of cosmic expansion. By measuring redshifts of many galaxies at various distances and determining their distances through other methods, like standard candles objects of known intrinsic brightness, astronomers can trace how the expansion rate has changed over cosmic history. These studies revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, made by studying distant supernova and measuring how their redshifts and distances deviated from what would be expected in a universe with constant or decelerating expansion. The acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy density and exerts a kind of repulsive effect that pushes space apart. This dark energy's influence has grown over cosmic time as the universe expanded and matter became more dilute. In the early universe, matter dominated and the expansion was slowing down. But a few billion years ago, dark energy became dominant and the expansion began accelerating. Distant galaxies' redshifts encode this history, showing patterns that reveal when the transition from deceleration to acceleration occurred. Redshift measurements also reveal structure in the universe. When astronomers measure redshifts for thousands or millions of galaxies, they can create three-dimensional maps showing how galaxies are distributed in space. These maps reveal the cosmic web, the filaments, walls, and voids that constitute the large-scale structure of the universe. Regions where galaxies are closely spaced show similar redshifts because they are at similar distances. Voids show up as redshift ranges where few galaxies appear. The chemical evolution of the universe is written in redshift as well. Spectroscopy of distant galaxies reveals what elements were present when that light was emitted billions of years ago. By comparing galaxies at different redshifts, different cosmic times, astronomers can trace how the abundance of heavy elements has increased over cosmic history as successive generations of stars created these elements through nuclear fusion and dispersed them through supernova explosions. Galaxies at Z equals 6 or 7 show much lower abundances of elements heavier than helium compared to nearby galaxies, confirming that the early universe was primarily hydrogen and helium, with heavy elements accumulating over billions of years. Even the shapes and types of galaxies change with redshift. High redshift galaxies tend to be smaller, more irregular, and more actively forming stars than low redshift galaxies. This reveals that galaxies evolve over time, growing through mergers and gradually building up their stellar populations. The universe at Z equals 2, when it was about 3 billion years old, was a much more turbulent place, with higher rates of galaxy interactions and star formation than the relatively sedate local universe we see today. Gravitational lensing affects redshift measurements in subtle ways. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity bends the light's path and can magnify the image. But it also affects the light's frequency. Different images of a gravitationally lensed galaxy, formed by light taking different paths around the lensing mass, can show slightly different redshifts due to the gravitational time dilation in the lens's gravitational field. These tiny differences help astronomers probe the distribution of mass in the lensing object. The reddening of distant galaxies is therefore not just an interesting observational fact, but a fundamental window into cosmic history. Every measurement of a galaxy's redshift tells us how far away it is, how long ago its light was emitted, and what the universe was like at that cosmic epoch. The systematic increase in redshift with distance directly demonstrates that the universe is expanding, that it had a beginning in the Big Bang, and that it's evolving over time. The precise pattern of redshifts reveals the expansion history, constrains the properties of dark energy, and allows us to trace the formation and evolution of structure across billions of years of cosmic time, making the reddening of distant galaxies one of the most information-rich phenomena in observational astronomy. where baby stars come from. Stars are not born in the bright, empty spaces between galaxies or in the clear voids of interstellar space. They emerge from darkness, from vast clouds of gas and dust that hang in the spiral arms of galaxies, regions so dense with obscuring material that they appear as black patches against the glowing background of the Milky Way. These stellar nurseries, called molecular clouds, are the cosmic wombs where stars begin their lives, places where gravity, temperature, pressure, and chemistry conspire to transform diffuse gas into brilliant spheres of nuclear fusion that will shine for millions or billions of years. The process begins with a molecular cloud, an enormous accumulation of gas and dust drifting through the galaxy. These clouds are cold, typically only 10 to 20 degrees above absolute zero, and they're composed primarily of molecular hydrogen, two hydrogen atoms bonded together, mixed with helium and trace amounts of heavier elements. The clouds also contain dust grains, tiny particles of silicates and carbon compounds, each grain smaller than a bacterium, but collectively making up about 1% of the cloud's mass. These dust grains play a crucial role despite their small mass contribution, shielding the interior of the cloud from starlight and cosmic rays, allowing it to remain cold enough for molecules to survive. Molecular clouds range in size from relatively small clouds, a few light years across, to giant molecular cloud complexes spanning hundreds of light years and containing enough material to form hundreds of thousands of stars. The Orion Molecular Cloud Complex, one of the nearest star-forming regions at about 1,300 light-years from Earth, contains enough gas to make roughly 100,000 stars, like the Sun. The cloud extends across much of the constellation Orion, with the famous Orion Nebula marking just one small region where star formation is particularly active and visible. For stars to form, something must disturb these clouds, compressing them beyond a critical threshold where gravity overwhelms the internal pressure that normally keeps the cloud stable. This compression can come from several sources. A shockwave from a supernova explosion, travelling through space at thousands of kilometers per second, can slam into a molecular cloud and compress it. The spiral density waves that create the spiral arms of galaxies compress gas as it enters these regions, triggering star formation that lights up the spiral arms with young, bright stars. Even the radiation and stellar winds from existing massive stars can compress surrounding gas, triggering new generations of star formation in a process that propagates through the cloud. Once a region of the cloud is compressed, gravity takes control. The denser parts of the cloud pull in surrounding material, growing denser still. This runaway process would cause the entire cloud to collapse into one enormous star, but molecular clouds are turbulent places, filled with eddies and currents of gas flowing in different directions. This turbulence, combined with the cloud's rotation and magnetic fields threading through it, breaks the cloud into fragments, each fragment typically containing anywhere from a fraction of a solar mass to tens of solar masses, becomes the seed of a star or a small system of stars. As a fragment collapses, it heats up. This might seem counterintuitive. How does something heat up as it collapses in the cold of space? The answer lies in gravitational potential energy. As gas falls inward, it accelerates, gaining kinetic energy. When fast-moving atoms and molecules collide with other particles, they convert their kinetic energy into thermal energy, heat. The center of the collapsing fragment grows hotter and denser, while the outer regions continue to fall inward, feeding the growing concentration at the center. The collapse doesn't proceed smoothly or uniformly. The fragment rotates, inherited from the overall rotation of the molecular cloud, and conservation of angular momentum means it spins faster as it shrinks, just as an ice skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the center. Instead, material settles into a rotating disk around the growing protostar, the nascent star at the center. This disk, called a protoplanetary disk or protostellar disk, channels material toward the protostar, while the outer parts remain in orbit, eventually becoming the raw material from which planets might form. The young protostar, deeply embedded in the infalling gas and dust, is invisible at optical wavelengths. The surrounding cocoon of material absorbs any visible light the protostar emits and re-radiates it as infrared radiation. This is why infrared telescopes are essential for studying star formation. They can penetrate the dust and observe the protostars hidden within molecular clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed thousands of these embedded protostars, showing snapshots of stars at various stages of formation. As the protostar continues to accrete mass, its central temperature and pressure climb steadily. The journey from cold molecular gas to a hot protostar takes roughly 100,000 years for a Sun-like star, though this timescale varies depending on the protostar's mass. More massive protostars collapse more quickly because their stronger gravity accelerates the infall. Less massive protostars take longer, sometimes millions of years, to fully form. The protostar doesn't simply accrete all the material that falls towards it. Young protostars are violent, magnetically active objects. Magnetic field lines threading through the protostar, and its disk can become twisted and tangled by the rotation. And these magnetic fields launch jets, narrow beams of gas that shoot outward from the protostar's poles at speeds of hundreds of kilometers per second. These jets are one of the most distinctive signs of active star formation. The Hubble Space Telescope has captured stunning images of these jets, often light years long, streaming away from young stars still hidden within their dusty cocoons. The jets serve an important function. They carry away angular momentum and energy that would otherwise prevent further accretion. Without some mechanism to remove angular momentum, the disk would simply spin faster and faster, and material would stop falling onto the protostar. The jets, along with stellar winds, outflows of gas from the protostar's surface, solve this problem, allowing the protostar to continue growing even as it spins. Where the jets slam into the surrounding molecular cloud, they create glowing knots and filaments called Herbig-Haro objects, named after astronomers George Herbig and Guillermo Haro, who studied them in the 1950s. These objects glow because the jet's high-speed collision with the ambient gas heats it to thousands of degrees, causing atoms to emit light. Herbig-Haro objects can move visibly over timescales of years, and they serve as signposts marking regions of active star formation. The accretion phase lasts for roughly 1 million years, though again this varies with stellar mass. During this time, the protostar is not yet a true star because no nuclear fusion occurs in its core. It shines from gravitational energy. The energy released as material falls onto its surface, and as it slowly contracts under its own weight. This contraction, described by Hermann von Helmholtz and Lord Kelvin in the 19th century, heats the interior gradually. Eventually, after millions of years of contraction and heating, the core temperature reaches approximately 10 million degrees Celsius. At this critical temperature, protons moving at extremely high speeds collide with enough energy to overcome their mutual electrical repulsion and fuse together, creating helium and releasing energy. This ignition of hydrogen fusion marks the birth of a true star. The protostar becomes a main sequence star, entering a stable phase where the energy released by fusion creates outward pressure that balances gravity's inward pull. For a star like the Sun, this moment arrives roughly 10 million years after the initial collapse began. The newly formed star is now generating its own energy through nuclear reactions rather than relying on gravitational contraction. It will remain on the main sequence, fusing hydrogen in its core for about 10 billion years, 100 times longer than it took to form. Not all fragments in a molecular cloud form single stars. Many form binary or multiple star systems, where two or more stars orbit each other. The fragmentation process can produce two separate cores within a single disk, each growing into a star. Or a protostellar disk can become gravitationally unstable and fragment, forming additional stars. About half of all stars exist in binary or multiple systems, making our single sun somewhat unusual. The smallest fragments don't have enough mass to ever ignite hydrogen fusion. Objects below about 0.08 solar masses, roughly 80 times Jupiter's mass, never reach core temperatures high enough for hydrogen fusion. These failed stars, called brown dwarfs, glow dimly from their residual heat and from the fusion of deuterium, a heavy isotope of hydrogen that fuses at lower temperatures than normal hydrogen. Brown dwarfs slowly cool over billions of years, gradually fading from view. The most massive fragments form massive stars, objects with tens of times the sun's mass. These stars form quickly, sometimes in just a few 100,000 years, and burn brilliantly but briefly. They produce intense ultraviolet radiation that ionizes the surrounding gas, creating glowing H2 regions like the Orion Nebula. The radiation pressure from these massive stars is so strong that it can halt further star formation nearby, blowing away the remaining gas and effectively shutting down the stellar nursery. The wind and radiation from massive young stars create expanding bubbles in the molecular cloud, clearing out regions and compressing gas at the bubble's edges. This compression can trigger new star formation, creating generations of stars, with the oldest stars at the center and progressively younger stars toward the periphery. The entire process is self-propagating until the molecular cloud is either dispersed entirely or exhausted of dense gas. When the most massive stars explode as supernovae after just a few million years, they inject tremendous energy into their surroundings, heating and dispersing the remaining molecular cloud and enriching it with heavy elements created in the star and in the explosion. The shockwave from the supernova can compress nearby clouds, triggering new rounds of star formation. In this way, star formation is a cyclical process. Stars form from clouds, massive stars disrupt clouds, supernova shockwaves compress new clouds, and stars form again. The entire life cycle from molecular cloud to dispersed star cluster takes roughly 10 to 20 million years. The Orion Nebula, one of the most famous star-forming regions visible to the naked eye, contains stars that are only about 1 to 2 million years old, cosmic newborns still surrounded by the glowing remnants of the cloud that birthed them. Over the next few million years, the radiation from these young stars will disperse the remaining gas, leaving behind a star cluster that will gradually spread apart as its members drift through the galaxy. Understanding where baby stars come from means understanding one of the fundamental cycles of the cosmos. The gas from which stars form was once inside previous generations of stars. Those stars fused hydrogen into helium, helium into carbon and oxygen, and heavier elements still, then returned that enriched material to space through stellar winds and supernova explosions. That material mixed into molecular clouds and became incorporated into new stars, including our Sun, which formed about 4.6 billion years ago from a molecular cloud that contained the ashes of earlier stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stars that formed, lived, died, and seeded the molecular cloud from which the Sun and Earth eventually emerged, continuing the ancient cycle of stellar birth and death that has shaped the galaxy since stars first began forming over 13 billion years ago. Why nothing can go faster than light? Light moves at exactly 300,000 kilometers per second in a vacuum, fast enough to circle Earth more than 7 times in a single second. This speed seems arbitrary at first, just another number to memorize. But the speed of light represents something far more profound than a mere velocity. It's a fundamental limit built into the structure of the universe itself, a cosmic speed limit that nothing with mass can reach, let alone exceed. Understanding why nothing can go faster than light means understanding one of the most revolutionary insights in physics, that space and time are not separate, unchanging backdrops to events, but are woven together into a unified fabric that behaves in deeply counterintuitive ways. Before Albert Einstein published his special theory of relativity in 1905, most physicists assumed that velocities simply added together in straightforward ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, then someone standing beside the tracks would see the ball moving at 70 kilometers per hour. This common sense addition of velocities works perfectly well at everyday speeds. But Einstein realized that this intuitive picture breaks down at velocities approaching the speed of light, and the breakdown reveals something fundamental about the nature of space and time. Einstein started with two basic principles. First, the laws of physics should be the same for everyone moving at constant velocity, regardless of how fast they're going. This principle of relativity had been around since Galileo, and it accords with common experience. You can't tell from experiments done inside a smoothly moving train whether the train is moving or the station is moving past you. Second, and more radically, Einstein proposed that the speed of light is the same for everyone, regardless of how fast they're moving or how fast the light source is moving. This second principle contradicts our everyday intuition about velocity addition. If you're on a train moving forward and you shine a flashlight forward, you might expect someone on the platform to measure the light going faster than someone on the train would measure it, by an amount equal to the train's speed. But experiments repeatedly showed that this doesn't happen. The person on the platform and the person on the train both measure exactly the same speed for the light. This bizarre result seems impossible if we assume that space and time are absolute and unchanging. Einstein's breakthrough was realizing that space and time must not be absolute. Instead, they must adjust themselves to keep the speed of light constant for all observers. When you move faster, time actually slows down for you relative to someone standing still, and distances contract in your direction of motion. These effects, called time dilation and length contraction, are not optical illusions or measurement errors. They're real physical changes in how time flows and how space extends. At everyday speeds, these relativistic effects are incredibly tiny, too small to notice. A person traveling in a car at highway speed experiences time flowing more slowly than someone standing still, but the difference amounts to only billionths of a second over a lifetime. But as speeds approach the speed of light, these effects become dramatic. At 90% of light speed, time runs at only about 44% of the normal rate. At 99% of light speed, time runs at about 14% of normal. As you get closer and closer to light speed, time slows down more and more dramatically, approaching a complete stop as velocity approaches the speed of light. This time, dilation has been confirmed through countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount Einstein's equations predict. Particles called muons, created when cosmic rays strike the upper atmosphere, live for only about 2 microseconds before decaying. At the speeds they travel, close to the speed of light, time dilation extends their lifetimes enough that they reach the ground before decaying, something that would be impossible if time flowed normally for them. GPS satellites must account for relativistic time dilation, both from their speed and from Earth's gravity, or they would accumulate errors of several kilometers per day. Length contraction is equally real. A spaceship traveling at 99% of light speed would be compressed to about 14% of its rest length in the direction of motion from the perspective of someone watching it pass by. From the crew's perspective, inside the ship, they wouldn't feel compressed. They would measure their ship as having its normal length. but they would measure the distance to their destination as being contracted, appearing much shorter than it does to someone at rest relative to the destination. These strange effects arise from the fact that the speed of light must be the same for everyone. If you're chasing a beam of light at 99% of light speed, you still measure that light beam as moving away from you at full light speed, not at 1% of light speed, as you might expect. This only makes sense if time is flowing more slowly for you, and distances are contracted in your reference frame. The adjustments exactly compensate to keep the speed of light constant. But what happens if you try to accelerate something to light speed? Here's where the cosmic speed limit becomes absolute. As an object with mass accelerates, it gains kinetic energy. In classical physics, kinetic energy depends on velocity in a simple way. Double the velocity, and kinetic energy increases by a factor of 4. But Einstein showed that the relationship changes as you approach light speed. The energy required to accelerate an object increases more and more dramatically as velocity increases, and as you approach light speed, the energy required approaches infinity. This happens because of something called relativistic mass increase. As an object moves faster, it becomes harder to accelerate. It behaves as if it's getting more massive. At 90% of light speed, an object has about twice its rest mass. At 99%, it has about 7 times its rest mass. As velocity approaches light speed, the relativistic mass approaches infinity. To actually reach light speed would require infinite energy to accelerate infinite mass, a physical impossibility. Light itself travels at light speed because photons, the particles of light, have no mass. Maxwell's equations, which describe how electromagnetic fields behave, predict that electromagnetic waves travel at a specific speed determined by properties of space itself. Einstein realized that this speed is the cosmic speed limit, and that massless particles must travel at exactly this speed. Photons don't have to accelerate to light speed. They're created already moving at light speed, and they can never slow down or stop as long as they exist. Other massless particles like gluons, which carry the strong nuclear force, also travel at light speed. Gravitational waves, ripples in space-time itself, travel at light speed as well. Mass is what prevents particles from reaching this ultimate speed. Any particle with mass can approach light speed arbitrarily closely if given enough energy, but can never quite reach it. The relationship between energy, mass, and velocity is captured in Einstein's famous equation, E equals mc squared, though this is actually a special case of a more general equation. The full equation shows that total energy equals the rest mass energy plus kinetic energy, and as velocity increases, more and more of the total energy goes into the kinetic energy component. At very high velocities, most of the energy is kinetic rather than rest mass. Particle accelerators demonstrate these principles directly. The Large Hadron Collider accelerates protons to more than 99.99% of light speed. At these velocities, the protons have about 7,000 times more energy than their rest mass energy. Accelerating them to even higher velocities, getting closer to light speed, requires exponentially more energy for each incremental increase in velocity. No matter how much energy you put in, the protons never quite reach light speed, and the energy required to actually reach it would be infinite. Some people wonder whether traveling faster than light might be possible by warping space rather than moving through it. General relativity does allow for exotic spacetime geometries, like wormholes or warp drives, that could theoretically allow effective faster-than-light travel without actually moving through space faster than light. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to contract space in front of a spacecraft and expand it behind, allowing the spacecraft to effectively travel faster than light while locally moving slower than light relative to the space immediately around it. However, These solutions require exotic matter with negative mass or negative energy density, properties never observed and possibly forbidden by quantum mechanics. Even if such matter could exist, the energy requirements would be astronomical, potentially requiring more energy than exists in the entire observable universe. These remain purely theoretical concepts, with no practical pathway to implementation, and they don't violate the fundamental principle that nothing can move through space faster than light. The cosmic speed limit has profound implications for space travel. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Travelling to the centre of our galaxy would take over 25,000 years at light speed. Reaching nearby galaxies would take millions of years. The vast distances between stars and galaxies, combined with the absolute speed limit, mean that interstellar travel remains extraordinarily challenging even in principle. For travellers moving at near-light speeds, time dilation provides a partial solution. From the crew's perspective, a journey might take only months or years, while decades or centuries pass on Earth. This time dilation allows relativistic travellers to cross vast distances within their own lifetimes, though everyone they knew would age far more or be long dead by the time they returned. This creates a fundamental asymmetry. The traveller's time and the stay-at-home's time flow at different rates, and there's no way to make them match up again. The speed of light also limits how quickly information can travel. When you see a star in the night sky, you're seeing it as it was years or centuries ago. That's how long the light took to reach you. The sun you see is 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. This light travel time creates what physicists call a light cone, the boundary between events that can influence you and events that cannot because they're too far away in space and too close in time for light to have travelled from there to here. Causality itself depends on the cosmic speed limit. If information could travel faster than light, it would be possible to send messages backward in time, to communicate with your own past. This creates logical paradoxes, like sending a message to your past self, telling yourself not to send the message. The speed of light limit prevents these paradoxes by ensuring that cause always precedes effect for all observers, regardless of their motion. The universe seems designed in a sense with this speed limit built in. Light speed isn't just the speed at which light happens to travel, it's a fundamental property of space-time itself, woven into the structure of reality. Mass is what prevents particles from reaching this ultimate speed, and the closer you get to it, the more energy is required to go faster, asymptotically approaching infinite energy at the limit. This speed limit connects space and time in an intimate way. Space and time aren't separate entities but are aspects of a unified, four-dimensional space-time. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. The cosmic speed limit defines the structure of this space-time, determining how space and time mix together as observers change velocity. Why nothing can go faster than light ultimately comes down to the structure of space-time itself. The speed of light isn't a speed limit in the sense of a rule imposed from outside. It's a fundamental property of how the universe is built, how space and time relate to each other, and how energy and mass behave. Reaching light speed would require infinite energy. The only things that can travel at light speed are things with no mass, like photons, which must always travel at this speed. Everything else, everything with mass, can only approach this ultimate velocity, forever accelerating, but never quite reaching the cosmic speed limit that defines the maximum rate at which anything can travel through the fabric of space-time. Why moons orbit in perfect circles? When you look at diagrams of moons orbiting planets, they're often depicted as perfect circles with the planet at the centre. This image is actually misleading. No moon orbits in a perfect circle. Every orbit in the universe, whether it's a moon around a planet around a star, or a star around a galaxy's centre, follows an ellipse. a stretched circle with the central body at one of the ellipse's two focal points, not at the center. However, many moon orbits are remarkably close to circular, so nearly circular, that the deviation is barely noticeable. Understanding why some moons have nearly circular orbits, while others follow elongated ellipses, means understanding orbital mechanics, tidal forces, and the long-term evolution of gravitational systems. The fundamental laws governing orbital motion were discovered by Johannes Kepler in the early 17th century, based on meticulous observations of planetary positions compiled by Tycho Brahe. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus. This applies equally to moons orbiting planets. An ellipse is characterized by its eccentricity, a number between 0 and 1. An eccentricity of 0 represents a perfect circle. An eccentricity close to 0 represents a nearly circular ellipse. Higher eccentricities produce more elongated ellipses, and an eccentricity of 1 represents a parabola, an open curve, not a closed orbit at all. Earth's moon has an orbital eccentricity of about 0.0549, meaning its orbit is quite close to circular but noticeably elliptical. At its closest approach, called perigee, the moon is about 363,000 kilometers from Earth. At its farthest point, called apogee, it's about 405,000 kilometers away, a difference of about 42,000 kilometers, or roughly 11%. This variation causes the moon's apparent size in Earth's sky to change noticeably over the course of a month. A full moon at perigee appears about 14% larger in diameter than a full moon at apogee, the so-called supermoon phenomenon. Many other moons have far more circular orbits than Earth's moon. Jupiter's major moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, all have very low eccentricities. Io's eccentricity is about 0.0041, Europa's is 0.009, Ganymede's is 0.0013, and Callisto's is 0.0074. These are remarkably circular orbits, with the differences between closest and farthest approaches being only tiny fractions of the orbital radius. Saturn's largest moon, Titan, has an eccentricity of 0.0288, still quite circular, though less so than Jupiter's major moons. The reason many moons approach circular orbits lies in tidal forces and the dissipation of energy over time. When a moon orbits a planet on an elliptical path, its distance from the planet changes continuously. As the distance changes, so does the strength of the tidal forces between the planet and moon. Tides work both ways. The moon raises tides on the planet, and the planet raises tides on the moon. These tidal bulges require energy to create because they deform the bodies involved, flexing and stretching them. For a moon in an eccentric orbit, the tidal bulges change in size as the moon moves closer to and farther from the planet. This continuous flexing dissipates energy as heat through internal friction, the same mechanism that makes a rubber ball warm up when you repeatedly squeeze and release it. This tidal heating is not a small effect. Jupiter's moon, Io, experiences such intense tidal heating due to its slightly eccentric orbit that it's the most volcanically active body in the solar system, with lava lakes, erupting volcanoes, and a surface constantly renewed by volcanic activity. The energy dissipated through tidal heating doesn't disappear. It comes from the orbital energy of the moon. As orbital energy is lost, the characteristics of the orbit change. Specifically, the eccentricity decreases. The orbit becomes more circular. This process, called tidal circularization, operates on timescales of millions to billions of years, gradually transforming elliptical orbits into nearly circular ones. The timescale depends on the masses involved, the distances, the physical properties of the bodies, how easily they deform, and the initial eccentricity. Earth's moon provides a clear example of tidal evolution, though in the moon's case the effect is primarily in the exchange of angular momentum rather than circularization. The moon raises tides on Earth, the familiar ocean tides that rise and fall twice daily. Earth's rotation carries these tidal bulges slightly ahead of the Earth-Moon line because of friction and the time it takes for water to respond to the tidal forces. This offset means the tidal bulges pull on the moon, accelerating it in its orbit and causing it to gradually move away from Earth at about 3.8 centimeters per year, a rate precisely measured by bouncing laser beams of retroreflectors left on the moon by Apollo astronauts. As the moon moves outward, Earth's rotation slows down to conserve angular momentum. Earth's day gradually lengthens, currently by about 1.7 milliseconds per century. This process has been operating for billions of years. Early in Earth's history, when the moon was much closer, tidal forces were far stronger. Days were much shorter, perhaps only 5 to 6 hours, and the moon orbited much faster and on a more eccentric orbit. Over billions of years, tidal forces circularized the moon's orbit to its current low, but non-zero eccentricity. The moon's orbital eccentricity isn't zero because the circularization process hasn't completed and perhaps never will. The sun's gravitational pull perturbs the moon's orbit, periodically increasing its eccentricity slightly. These perturbations compete with the tidal circularization, creating a balance that maintains a small but non-zero eccentricity. Additionally, the ultimate end state of tidal evolution is tidal locking, where the moon always shows the same face to the planet, and the planet's rotation period equals the moon's orbital period. Earth's moon is already tidally locked to Earth, but Earth is not locked to the moon. Eventually, if given enough time, Earth would become locked to the moon as well, with both bodies always showing the same faces to each other, though this would take tens of billions of years, longer than the sun's remaining lifetime. Some moons maintain eccentric orbits despite tidal forces because of orbital resonances with other moons. Jupiter's moons Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonance was discovered by Pierre-Simon Laplace in the 18th century. The gravitational interactions in this resonance maintain Io's and Europa's orbital eccentricities even as tidal forces try to circularize them. The result is continuous tidal heating, keeping Io's interior molten and likely maintaining a subsurface ocean on Europa beneath its icy crust. Saturn's moon Enceladus experiences similar effects. Its orbital eccentricity of about 0.0047 seems small, but it's sufficient to generate significant tidal heating in this small moon. Enceladus orbits in a 2-to-1 resonance with the larger moon Dione. The resonance prevents the orbit from fully circularizing, maintaining just enough eccentricity to produce tidal heating that keeps a subsurface ocean liquid beneath Enceladus's southern polar region. Geysers of water erupt through cracks in the ice, spraying material into space and creating Saturn's E-ring. New moons in eccentric orbits take time to circularize. If a moon forms from a giant impact, as Earth's moon likely did, the debris initially orbits in highly eccentric, chaotic paths. Over time, collisions between orbiting fragments dissipate energy and circularize the orbits, while material gradually coalesces into a single moon. The moon starts with a moderately eccentric orbit that gradually becomes more circular through tidal interactions. Young moons should have more eccentric orbits than old moons, all else being equal. Captured moons often retain eccentric orbits. When a planet gravitationally captures a passing asteroid or comet, the capture typically results in a highly eccentric orbit. Without significant tidal forces or atmospheric drag to circularize the orbit, it remains eccentric indefinitely. This is why many of the small, irregular outer moons of the giant planets have highly eccentric orbits. They're captured asteroids, or Kuiper belt objects that have never undergone significant tidal circularization. Mars's two small moons, Phobos and Deimos, are thought to be captured asteroids, though their orbits are fairly circular, suggesting either that they've been in place long enough for tides to act or that they were captured through an unusual mechanism that placed them in nearly circular orbits initially. The mathematical framework for understanding orbital evolution through tides was developed in the 19th and 20th centuries by George Darwin, son of Charles Darwin, and others. The tidal quality factor, denoted Q, quantifies how efficiently a body dissipates tidal energy. Bodies with low Q dissipate energy efficiently, leading to faster orbital evolution. Rocky bodies typically have Q values of 10 to 100. Gas giants have Q values around 10,000 to 100,000 because gases don't maintain permanent tidal bulges as efficiently as solid or liquid bodies. These Q values determine how quickly orbits evolve. Computer simulations of moon system evolution incorporate tidal effects, gravitational interactions between multiple moons, and perturbations from the Sun and other planets. These simulations show that systems naturally evolve toward configurations with circular orbits, tidal locking, and often orbital resonances. The solar system's moon systems we observe today represent billions of years of this evolution, with orbits that have circularized, resonances that have captured moons into stable configurations, and tidal locking that has synchronized rotations. Some moons will never fully circularize their orbits because external perturbations constantly act to increase eccentricity. The moon's orbit around Earth is perturbed by the Sun, creating periodic variations in eccentricity over 27.5-day cycles. Neptune's moon Triton orbits in a retrograde direction, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton's orbit has circularized over billions of years to an eccentricity of only 0.000016, one of the most circular orbits known, but the orbit is also slowly decaying. Tidal forces are causing Triton to spiral inward, and in about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system. The appearance of circular orbits in diagrams and popular depictions stems from the fact that many major moons genuinely have nearly circular orbits. Eccentricities low enough that drawing the ellipse versus a circle would show barely any difference. For Ganymede, with its eccentricity of 0.0013, the difference between the orbit's longest and shortest diameters is only 0.26%. Drawing this accurately would require extraordinary precision. For practical purposes, these orbits are functionally circular, even though they're technically ellipses. Perfect circles don't exist in orbital mechanics because achieving exactly zero eccentricity requires perfectly balanced initial conditions and no subsequent perturbations. Conditions that never occur in nature. But through billions of years of tidal evolution, many moons have achieved orbits so close to circular that they serve as excellent approximations shaped by the patient, inexorable work of tidal forces, dissipating energy, transforming the chaos of formation into the elegant, nearly circular orbits that characterize mature moon systems throughout the solar system, demonstrating how gravitational interactions over immense timescales can organize and simplify what begins as disorder, creating the stable, predictable, celestial mechanics that allow us to calculate moon positions years or centuries into the future with extraordinary precision. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-cell to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure, favouring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favoured adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favour more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provided advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favour the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations. Oxygenic photosynthesis, or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice. Each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe.